Hi, it's time for another math easy solution. Today I'm going to go over further into vectors and the geometry of space, and this time look at the cross product. Alright, so let's jump right in, and note, as always, if you don't have time to watch this whole video, you can play this video at a faster speed, and here's a tutorial on it. And pretty epic life hack. Your brain gets used to faster speed. And also you could download and read the notes, and also read the notes on the Hive blockchain, or watch the video parts, or watch the video in parts. All the links to all these will be in the description below, including the timestamps, as well as the notes in the Hive blockchain and the downloadable PDF notes. Anyways, let's jump right in. Alright, so calculus book reference, and note that I mainly follow along the following calculus book. This is Calculus Early Transcendental 7th edition by James Stewart, and note in the earlier videos I used the 6th edition. And again, this is a useful tip here, because you can always just skip these introductions that I have, and you can go straight to whichever timestamp you want. Anyways, next part here, sections in calculus book chapter. So I've made a list of the sections in this particular chapter with links to the Hive post of the videos I have already finished. And so this is the chapter Vectors and the Geometry of Space. And here's a link to, this is 3D coordinate systems, there's vectors, then there's complex numbers as rotation matrices, and the dot product was the last video, and now the current one is the cross product, and that's a current video, and then these ones will be in the future ones. Alright, so let's jump right in. Alright, so topics to cover in this video, so note that the timestamps will be included in the video description for each topic listed below. So we're going to go over the cross product, its definition, and also a historical note on Sir William Rowan Hamilton. And then we'll go over determinants, and then cross product in determinant form. We'll go over example 1, example 2, and then cross product orthogonality, or perpendicular proof. And then go over theorem 1, and then look at the right hand rule, and then cross product rule length, and then theorem 2. And then go over the corollary, and then just the corollary theorem, and then the geometric interpretation of theorem 2. Yes, and then go over example 3, example 4, and then look at properties of the cross product, theorem 3, then proof of property 5. Actually, this is, proof of property 5 in this theorem right here. And this theorem here has, I believe, 6 properties there. So then we'll go over triple products, and then formula of a parallelepiped, and then go over example 5, and then look at torque, example 6, and then go over some quick exercises. So exercise 1, 2, 3, 4, and then 5 is on vector triple product. And these exercises are actually just the proof of the properties in this theorem 3 there. Anyways, let's continue further. Alright, so let's jump right in. So the cross product, and that's this part right here. Alright, so the cross product given two non-zero vectors, we'll call this one A, which has the it has the terms A1, A2, and A3, and then the vector B, which has terms B1, B2, and B3. It is very useful to be able to find a non-zero vector C that is perpendicular to both A and B, as we will see in the next section and in future chapters. So if C is equal to C1, C2, and C3, and let's say this is such a vector that is perpendicular to both A and B, then A dot, so the dot product, has to equal to 0, A dot C, and in B dot C has to equal to 0, i.e. the dot product is 0 for perpendicular vectors, as in my earlier video on the dot product. So make sure to watch that one over there. So it has to equal to 0. And so what we have is, what we must have is the dot product. Let's go over the first one. So A vector dot C vector is equal to, well, let's write these, expand these out just because it's the beginning of the video, and then after we could skip a lot of the steps. So this is just going to be A1, A2, A3 dot, and write these in this bracket form for vectors, and this is C1, C2, C3, like that, and this equals to, well, each term, so we write the first term, A1 times C1, then it's going to be plus this term multiplied by this, and then this one multiplied by that. So it's going to be A1, C1 plus A2, C2 plus A3, C3. Now this has to equal to 0 if C is perpendicular to A. So we have that, and then likewise, similarly, the next one's going to be B like that, B dot C vector. So this equals to, we could write it out like that, but it's going to be the same thing. So we're just going to write this B1 C1, yeah, plus B2 C2 plus, this next one's going to be B3 C3. This has to equal to 0. So I'm just going to box these two formulas in, because this is what we are going to work with. So we're going to have to work with this and then eventually find the C1, C2, and C3 terms for the C vector, given this formula over there, these two formulas. All right, so let's continue further. So to eliminate the C3 there, what we can do, raise this dot, we can, to eliminate C3, we multiply the first equation right here by B3, and then the second one by A3. So then we'll have, and then we'll subtract. And when we do that, when we multiply B3 here, this A3, these ones are the same. So you could cancel these out when you subtract. So let's just do that with these equations. So what we get is, the first one's going to be, well, we're multiplying it by B3. So I'm going to put these in order. So if I have A1 there, then B is before C. So we'll write A1, B3, C1. So we have the same pattern we'll use throughout. And then A2, B3, and then C2. And then the next one's going to be A3, B3, C3. And this equals to, well, 0. Because you multiply this one also by B3. B3 times 0 is still going to be 0. So just multiply there. And then the next one is going to be, and we're going to be subtracting this whole thing from, well, this one here, multiply this out here. And then we're going to subtract it all. I'm going to write it like that so that put it all together. So the next one's going to be, the next one is here, B1, C1, but then we're multiplying that by A3. So we'll have A3 and then B1, C1, and then plus, let's remove this minus sign there because we will subtract like that from everything. And then it's going to be A3, and then B2, C2, and then plus, this is going to be A3, B3, C3 equals to 0. And then when we subtract everything here, we're going to, well, cancel these two out. And yes, we'll have that canceled out. And what we also have is, well, we have a C2, C2, and a C1, C1. We could factor those out. And this one we subtract 0 from 0 is just going to be 0. So we're going to have this equals 2, and I'll put this one on top there. Write it like this. A1, B3, and then because we're going to be factoring out the C1, subtracted by A3, B1. A3, B1, and this is going to be C1. And then the next one, similar with this C2 now. Because we're subtracting here, these ones all become negative at the bottom. So now this becomes, and then this is going to be plus A2, B3 minus, because we're subtracting everything, A3, B2. So notice we just switched these around. Notice there's an A1, this one's B1 at the bottom there. Then B3, A3, so the 1s and 3s switches. This one, 2, 3, becomes 3, 2. So we have this, and then this is factored out to C2, and the C3s are canceled. This equals to 0. All right, so we have this equation. I'm going to box this in like that. All right, so let's continue further. So the equation above has the form P, we'll call this P times C1 plus Q, there's this one in the bracket, it's Q, times C2 equals 0, for which an obvious solution is, and let's just write this down so it's easier to solve this. So PC1 plus, and if we write QC2, if this equals to 0, then well, we have to cancel this out. And one way is if the C1 is equal to Q, like that. And then if this C2 is equal to negative P, then we're just gonna have PQ minus PQ. Yeah, so this will cancel, equals to 0. So, yeah, in other words, what we'll get is, let's put this like this. Yeah, like this. This becomes just PQ minus, well, PQ equals to 0. So that is a solution. So that means that C1 is equal to Q. And in our case, Q is this right here, A2B3 minus A3B2. So this equals to A2B3, let's remove the bracket. A2B3 minus A3B2. So that is, this one is our C1. And then likewise our C2 is going to equal to negative P, so equals negative P, like this. And negative P is just, well, we know that that's just going to be, this is P, but we have to put the negative of it. So this equals 2, here let's put this negative, and then this is going to be P, so this is P there, A1, B3 minus A3, B1, so you can put the negative there, or equals 2, just put, remove the negative, multiply it inside, move this positive in front. So A3, B1 minus A1, B3. And you could tell the negative sign, this one here, a good way to remember this, is that notice there's an A2, then A3, but this one starts with an A3, A1. So in other words, we go from smaller A to bigger. This one we go bigger A to smaller when there's that negative. And this will come in handy throughout this video. All right, put the 3 like that, and box this in. All right, and now that we have these two formulas for C1 and C2, so substituting these values into either of the original equations, we then get, and these are the original equations, if we put in C1 and C2 in either one of these, we could solve for C3. Yeah, so let's look at the first equation and plug in our C1 and C2 inside. So what we get is, let's see that again, so A1, C1, and then A2, C2, and A3, C3. So we'll write A1, so A1, and then A1, and then C1. C1 is this part right there. Put A2, B3 minus, or actually, let's just write it out for completeness so we don't have to try to remember it. So A1, C1 plus A2, C2 plus A3, C3 equals to 0. So then what we'll get is A1 is going to equal to A2, B3 minus A3, B2, and then plus A2, and then we'll plug in our C2, which is this A3, B1. A3, B1 minus A1, B3, and then plus A3, C3 equals to 0. All right, so now let's just do some expansion here. So then what we get is, put this like this. This becomes A1, A2, B3 minus A1, A3, B2, and then plus A2, A3, B1 minus, put the A2 inside after the A1, A2, B3, then plus A3, C3 equals to 0. So let's see if we could cancel some stuff out. Well, we have A1, A2, B3, and A1, A2, B3. This cancels. So we canceled those, and now we could see here every single remaining term has an A3 there. So that means we can, well, divide out everything by A3. In other words, we could just cancel the A3, cancel the A3, cancel the A3. Because we could divide that whole thing out by A3. So we get now is, well, this becomes, and let's just write what we have, and I'll put this one, I'll put that one in front. So minus A1, B2 plus, and then this plus is A2, B1, and then plus C3 equals 0. So in other words, now we just move these over to the other side. In other words, these just switch signs. So what we get is, lastly, so we switch signs. This becomes C3 is equal to A1 becomes positive, B2, then minus A2, B1. Like that. Fascinating stuff. All right, so this means that a vector perpendicular to both A and B is our C vector. C, and then this one is, write these in terms of the triangle brackets, C1, C2, and C3, and we know each one of these terms. C1 is equal to A2, B3 minus A3, B2. It becomes A2, B3 minus A3, B2. And then the next one's going to be, well, this minus sign there. And that kind of flips the order around. So instead of A1, we'll go with A3. A3, B1, and then A1, B3. So notice there's a pattern that's arising. A3, B1 minus A1, B3. Yeah, and then the last one is a C3. That's going to be this A1, B2 minus A2, B1, close bracket. And the resulting vector is called the cross product of A and B, and is denoted by A and then this X-like character called cross. So A cross B. And that brings us to this definition of the cross product. So if A is equal to, is a vector with the terms A1, A2, A3, and B has terms B1, B2, B3, then the cross product of A and B is the vector. Yeah, the vector, let's write this down. A vector cross B, which is the cross product of A and B. This equals 2, and that just equals to this whole term over there. So A2, B3 minus A3, B2. And then the next one is going to be, well, A3, B1 minus A1, B3, and then goes back to now starting with the lower number A1, then A2. A1, B2 minus A2, B1. Like that. Alright, let's go over some more notes. So notice that the cross product A cross B of two vectors A and B, unlike the dot product, is a vector. For this reason, it is also called the vector product. And also note that A cross B is defined only when A and B are three-dimensional vectors, which is interesting. Note there. Alright, and now let's go over a brief historical note. This is on Sir William Rowan Hamilton. Yeah, so the cross product was invented by the Irish mathematician Sir William Rowan Hamilton, born either 3rd or 4th August 1805, and died September 2nd, 1865, who had created a precursor of vectors called quaternions. When he was 5 years old, Hamilton could read Latin, Greek, and Hebrew. At the age 8, he added French and Italian, and when he was 10, he could read Arabic and Sanskrit. Sanskrit, which is some pretty ingenious fellow here. At the age of 21, while still an undergraduate at Trinity College in Dublin, Hamilton, and yeah, here's at Ireland. So Dublin is in Ireland. So yeah, so at Trinity College in Dublin, Ireland, Hamilton was appointed professor of astronomy at the University and Royal Astronomer of Ireland. Epic stuff here. Alright, now let's continue further, and this time look at determinants. So in order to make the definition easier to remember, we use the notation of determinants. A determinant of order 2 is defined by, and we'll write this like this, you have A, B, and then C, D, and put these brackets like that in matrix form. This equals to, well, A times D minus B times C. In other words, we'll have A, D, minus B, C, like that. And notice the cross. Hence why it's called cross product, as we'll get to. So it switches up like that. And for example, just to illustrate this, if we have this determinant 2, 1, and then negative 6, 4, this equals to, well, 2 times 4 minus, and then 1 times negative 6. Like that. This equals to, well, 8 minus negative 6, that becomes plus 6. So this equals to 14. So 8 plus 6 is positive 14. And now looking at a determinant of order 3, this is order 2 or 2 dimensions. Now look at 3 dimensions. This can be defined in terms of second order determinant as follows. So 3-dimensional one will be written as, say you had an A1, A2, A3, the next one's B1, B2, B3, next one's C1, C2, C3. Put it like this. This equals 2 is defined as A1 times the second order determinant, which we know how to solve by this definition. This becomes, so it is A1, the next one is going to be, we'll box these in like that. This is going to be B2, B3, C2, and then C3. And then the next one is going to be actually minus, just to match up with our cross product. This next one's going to be A2, like that. Erase this. A2, and now instead of that one, we'll look at this and these two. This is going to be B1, B3, C1, C3. And then the next term is going to be, well, plus A3, and it's going to be similar to the A1 setup. Here's shifting everything over, erase this, erase this. This is going to be this, and then we're going to box this into determinant. It's going to be A3, B1, B2, and then C1, C2, and then box that up. All right, and now observe that each term on the right side of the above equation, this right here, involves a number AI, so A1, A2, or A3, in the first row of the determinant. That's the one right here, A1, A2, A3, and is multiplied by the second order determinants, or determinant for each one. Multiplied by the second order determinant obtained from the left side by deleting the row and column in which A appears, or AI appears. In other words, if you have this A1 like that, is the first one, and you can get the determinant by eliminating the row and column in which AI appears. In other words, the first row is gone and the first column, so all you're left with is this, and that's this one right here. So we remove this, and then the next one is A2. We look at this, and then we eliminate this column and this row, and we're left with this, B1, C1, and then B3, C3, and that's just this right here. All right, and now let's do the next one. The next one is A3, so we do this and then eliminate this and this, so all we're left with is B1, B2, C1, C2, and that's exactly this right there. So that's fascinating stuff. All right, so erase that. And notice also the minus sign in this second term, and again, it's to match up with our cross product. So now, for example, let's take a look at an example, and we'll do this one here, 1, 2, negative 1. I'll make it more compact so we could fit it in. 1, 2, negative 1, and then 3, 0, 1, then negative 5, 4, 2, like that. Let's say we have this. This equals 2, well, we take the 1, eliminate everything else, left with this column right there. All right, so that's what we're left with. Let's write that in. This equals 2, 1, and then determinant of 0, 1, 4, 2. The next one is going to be minus. We take this one here, and then we eliminate this and this. All we're left with is this and this. All right, let's erase this, and we'll get a 2, and then we'll get a 3, 1, negative 5, 2, like that. And the next one's going to be this, eliminates this, we're left with this 3, 0, negative 5, 4. All right, so this is going to be minus 1, and then 3, 0, negative 5, and 4, like that. And now we take the determinant of each one, so 1 times, well, 0 times 2 is 0, minus 1 times 4 is 4. And then the next one is, well, negative 2, and then times it by 3 times 2 is 6, minus 1 times negative 5 is going to be, 1 times negative 5 is negative 5, but then we're minusing that, so it's going to be plus 5, like that. So plus 5. And then the next one is going to be plus, we'll just put a negative 1 like this. Yeah, plus that, or I'll just put a minus 1 there, because that's just minus 1 over there. And this becomes 3 times 4 is 12, minus 0 times 5 is 0. All right, so now we get this. This equals to negative 4 times 1 is just negative 4. And this one is going to be negative 2 times 11. It's going to be negative 22. Next one's going to be minus 12. This equals to, these are all minus. 22 minus 12 is going to be 34, negative 34. Then minus 4 is going to be negative 38. Amazing. Alright, so now that we've got over this determinant of order 3, and now we're going to look at the cross product and write it in that determinant form. So now if we now rewrite the definition of the cross product using second order determinants and the standard basis vectors I, j, and k, remember these are the vectors in the x, y, and z direction, and these are all of unit length, in other words length 1. So we see that the cross product of the vectors a with the terms a1i plus a2j plus a3k and b vector, which equals to b1i plus b2j plus b3k. Again, it's from my earlier videos. Make sure to look that up. Yeah, so now we could write our cross product as, so we have a vector cross b vector. This equals to, and let's go back to our definition. So we wrote down a definition here. This equals to the terms. This is the I terms, this is the j, this is the k. So a2b3 minus a3b2, etc. And this was a3b1 minus a1b3. Again, these are just determinants of order 2, but then we're going to have to multiply it out. And we're going to multiply it out in vector form. So I'll show you what this will equal to. So we're going to write it in terms of this right here. But again, we have a and b instead of the c vector. So what we'll write here is this is actually equal to a2, a3, and then this is going to be b2, b3. Then this is going to be the I vector. And to see that here, because remember, this just equals to a2, a3, so multiply this by this, and then minus this by this. In other words, that equals to a3, b3, I mean a2, b3 minus a3, b2, and this is in the x coordinate there, or the x-axis there. This is a2, b3 minus a3, b2, and going back to the definition, that's this right here. And then we multiply by the I, so that it's the x-axis direction there. Then this one's going to be the j. This one's going to be a minus. Yes, this is the same thing as writing minus a1 b3 minus a3 b1, and so on. Exactly like the determinant definition for order 3. There's a minus there. So let's just keep writing it out. So this is going to be minus. So this is a2 a3. The next one, remember how this is. So you'll have this. And then cover it up. You'll have b1 instead of b1. We'll have a1, then a3, and then b1, b3, and so on. This is going to be a1, a3, b1, b3, and this is going to be our j, or the y axis. And again, this equals 2 with that minus sign. We'll have minus a1 times b3. So a1 times b3 cross minus a3 b1. Minus a3 b1. And then when you get rid of the minus sign, it becomes, well, this becomes plus. This is going to be a3, this becomes positive. a3 b1, this becomes negative. You put the negative inside. And that matches up again with the definition right here, a3 b1 minus a1 b3. And the next one is just the a1 b2 and then minus a2 b2. This is going to be plus, actually, whoops, we're not here, we're right here, plus, the last one is going to be a1, a2, b1, b2, and then this is going to be k vector. And again, for completeness, let's just write this out. The determinant of this is going to be a1 times b2 minus a2 b1. And again, going back to our definition, that is exactly this, a1 b2 minus a2 b1, and that's in the z-axis. This is the k is a z-axis vector. Alright, so now that we have this, and what we could do now is, in view of the similarity between the above equation and the third order determinant, we often write, because this one here, remember the determinant gives you a real number, but this one here, we just wrote it in this vector form. So instead of having this row as this number a1, a2, a3. So we'll get rid of the c1, move this, shift these two down, and then we'll put the I, j, k vectors on the top. So we could write this vector as, in determinant form, a cross b equals 2, and then we'll write I vector, j vector, k vector, and then we'll write a1, a2, a3, b1, b2, V3, like that. And yeah, so this determinant right here, you could apply the same rules, same definition, and you'll get to this setup here. And then you solve this one, you're going to get to the exact same definition over here. All right, so let's continue further. So although the first row of the symbolic determinant over here in the above equation consists of vectors, if we expand it as if it were an ordinary determinant of order 3, we will obtain our standard basis / second order determinant form right here. The symbolic determinant formula is probably the easiest way of remembering and computing cross products, and indeed it is. So now let's take a look at an example here. So example 1. So if A vector has the terms 1, 3, 4, then B has 2, 7, -5, compute the cross product. So let's just write down our determinant form like this. So write that down. So we'll have A vector cross B vector. This equals to I, so I, J, put this closer, and then K. Then underneath is going to be 1, 3, 4, then 2, 7, -5. All right, so now this equals to, let's expand this out. So remember, you would highlight this one, cross out the row and column, and then determinant of this second order one. So let's just get rid of this. This is going to be 3, 4, 7, -5, and then I. The next one's going to be minus, and the same thing, cross out. We're going to be left with 1, 2, and then 4, -5. Cross this out, and then we're going to have 1, 4, 2, -5, like that. And put it like that. This is going to be J vector. Last one, K, is going to be this, cross out, left with 1, 3, 2, 7. Then 1, 3, 2, 7. And this one is the K vector, like that. So this equals 2. And let's just solve this out. So 3, the determinant of this one, 3 times -5 is going to be -15, minus 4 times 7 is going to be 28, like that. And this is the I vector, minus, next one's going to be 1 minus -5, it's going to be -5, minus 4 times 2 is going to be -8, J vector, and then plus, the next one's going to be 1 times 7, 7, minus 3 times 2 is 6, like this. And this is going to be our K vector, so this equals 2. So -5 minus 28, well, that's going to be viewed as -10. So -38, and then and then minus another 5. It's going to be -43. This should be -43I minus, and this one here is minus. It's what's going to be plus, and then 5 plus. -5 minus 8 is going to be. So this is going to be, so let's add 2, then 3 is 13. This is going to be 13J vector. And then the next one, 7 minus 6 is 1. Plus 1, K vector, like that. Now, you have K, or just you could remove the 1 or leave it. I'll just leave it there. All right, so that's what we have. Alright, so now that we have this, and remember the cross product gives a vector that's perpendicular to the two vectors A and B. So that's a vector right there. And now let's take a look at example 2. And this one says, show that the vector A cross A is equal to 0 for any vector in V3, or the set of all 3-dimensional vectors. Alright, so let's continue further. So solution. So if A is equal to A1, A2, A3, then the cross product of A cross itself, like this, is equal to, well, again, we'll just write it down in indeterminate form, I, J, K, then A1, A2, A3, and then we'll write A1, A2, A3 like that, and cross it. Alright, so now let's expand this out in the second order determinant form. Again, cross this and this, we'll get A2, and we'll get this one right here. And let's write that down. So A2, A3, A2, A3, and then this is going to be the I vector. Then minus, the next one's going to be, well, this and this. A1, A3, A1, A3. This can be J, like that. And here I just shifted everything over, and then the next one is going to be, well, this one here. It's always this A1, A2, etc. This can be A1, A2, A1, A2, and then K, like that. All right, now this equals 2. Well, we have A2 times A3. This is the determinant A2, A3. This in regular bracket. And then minus, so this one minus this one. And those are going to be the same thing. A2 minus A3, and then minus, well, A2 minus A3, or A3 minus A2. Just to have this one in the front. And it's the same thing. These still cross out. These are the exact same thing, so they just cancel out. Become 0. And so on. Just leave it like that. Minus, and the next one's going to be A1, A3, A1 times A3, minus A3, A1. Like that. And what I'll do is I'm just going to shift this over to here. This is going to be J. Like that. And then plus the next one's A1, A2 minus A2, A1, K. And all these just cancel. These are all the exact same terms. A1 and A3 is the same thing as A3, A1. These all cancel, cancel, cancel. And you're just going to be left with equals 2, 0, I, minus or plus, well, it doesn't matter what you do, so minus 0, J, plus 0, K. In other words, this is just a 0 vector. All the terms, all the terms are 0. And all these axes, and this is K. Like that. And we'll just box this out. So there is our proof. And I'll put a check mark as that is the proof that A cross A is equal to 0. Alright, so now that we have these two examples, let's continue further and now look at the cross product orthogonality, or let's probably pronounce that again, orthogonality proof or perpendicular proof. So we constructed the cross product A cross B so that it would be perpendicular to both A and B, and this is one of the most important properties of a cross product. So let's emphasize this and verify it in the following theorem and give a formal proof. So theorem 1, the vector A cross B is orthogonal to both A and B. And proof, in order to show that A cross B is orthogonal to A, we compute their dot products as follows. And again, if you recall from our earlier video, if the dot product is equal to 0, then that means the two vectors are orthogonal or perpendicular. So what we'll do here is, we're going to do A cross B dot A. And then we'll compute their dot product as follows. We'll have this here. So if it equals to 0, it is orthogonal. So this cross product dot A. Like that. Now this equals 2. Remember, this one in the IJK format, but I'm going to, instead of writing it like that, I'm going to write it like this and put that put it in determinant form like this. Remember how it was. This is A2, A3. And this is going to be B2, B3. Like that. So this is the same thing as writing I and another one J. I'm just put these in these components like this. And this one's going to be A1, A3. B1, B3. We'll put it like that. And also forget to put in minus. Remember, the middle one has a minus. So all we're doing is putting this exact same setup here, this right here, but instead of writing these IJK, was put the in the triangle bracket format for vectors. So A2, A3, B2, B3 is minus A1, A3, B1, B3. Next one's A1, A2, and so on. And this is going to be A1, A2, and then B1, B2. So we have this, and put the square bracket, the triangle bracket, and I'm going to shift this over, and now we're going to be dotting A. So dot A1, A2, A3. So that is the A vector. And remember what happens with dot product. All it is you multiply this A1 with this, and then you add all the terms. Remember, dot product is multiply each coordinate, and then add them all up to get a number. So this is going to be Well, this one here is a determinant, and this one is A2 times B3 minus A3 times B2. This is going to be A2 B3, and then A2 B3 minus A3 B2. Then multiply this by A1, which is this. Next one is this, and this, and this, and this, and so on. And add them all up. Alright, let's continue. This is going to be now minus A1 B3 minus A3 B1, and then multiply by A2. Like that. And the next one is, and I'm just going to get some more space here by shifting this over, and then plus A1 B2 minus A2 B1. This is going to be our A3, like that. Alright, so now we have this. These are all over there. And now let's multiply all these inside. So factor this all out. So A1 times inside is going to be A1 A2 B3 minus A1 A3 B2. The next one will multiply A2 inside. That's going to be A1 A2 B3 minus A2 A3 B1. The next one, last one, is going to be plus A1 A3 and then B2. Then minus A2 A3 B1. And now let's do some cancellation. So this one's A1 A2 A1 A2 B3. This one's A1 A2 B3 as a minus. This cancels. And now let's take a look at this one right here. A1 A3 B2. A1 A3 B2, and that's negative. This cancels. This cancels. Or better yet, make it a different cancellation line. I'll do line like this, line like this. And then last one, A2 A3 B1 minus, and this one's A2 A3 B1. And yeah, there's a mistake I made actually. And that mistake is that this negative here becomes positive like that. This is minus here, this one's minus, is positive. So this is A2 A3 B1, this is minus A2 A3 B1. So yes, this one is cross it out, and we could cross it out like this, put double X, just so it matches up. Alright, so that equals 0. So hence, these are orthogonal, because the dot product is equal to 0 as per my earlier video. So I'll do a check mark like that. That's proof for that. Alright, so now that we have shown that this cross product is orthogonal to A, you can do the exact same thing and then show that it's also orthogonal to B. So a similar computation shows that A cross B dot B is equal to 0. I'm not going to go over that. It's pretty much the exact same thing, but you just replace it. Instead of dot product with A, dot product with B. Then you can do the exact same thing, multiply by B, and everything just cancels out exactly as usual. Alright, let's go further. So therefore A cross B is orthogonal to both A and B. So here's a formal proof of that, even though we constructed it by defining that it's the dot product is equal to 0. But anyways, that was just a verification of it. So now let's take a look at the right-hand rule. So if A and B are represented by directed line segments with the same initial point as in the figure below, so here is A and B from the same point, directed line segments like that, A and B, as in the figure below, then the above theorem says that the cross product A cross B points in a direction perpendicular to the plane through A and B. So this is a plane like this. The cross product is going to be going up like this, and this is perpendicular to it. And I think the calculus book this n meaning normal to it or whatnot. The direction is going up. But anyways, that's A cross B is orthogonal to both of these, like that. Now this brings us to the right-hand rule. So it turns out that the direction of A cross B is given by the right-hand rule. So if the fingers of your right hand curl in the direction of a rotation through an angle less than 180 degrees from A to B. So if you have the angle A, the line A, the vector A, then angle from here, same thing as curling your right hand in the direction of this right here. So this one is counterclockwise. This is counterclockwise. So if this angle is counterclockwise, this is going to be your fingers like this, and then your thumb points in the direction of A cross B. Yeah, so your fingers, if they're rotating in the direction from A to B, the angle, then your thumb points in the direction of A cross B. So yes, and then if you were to do B cross A, it would go from here to here, and your thumb would go downwards. and you'll have a negative cross product, which is interesting. Or a negative relative to this plane. In other words, it's going to go downwards. Anyways, that is an interesting right-hand rule, and we'll be needing that soon. So let's continue further. So cross product length. Now that we know the direction of A cross B, the remaining thing we need to complete is its geometric description is its length A across B, and then this absolute value sign, or just the length of it. Or in other words, how long is this vector? What's the magnitude of that length? So this is given by the following theorem. This is theorem 2. So if theta is the angle between A and B, so that theta is less than pi, or 180 degrees, or pi radians, and greater than or equal to 0, so less than or equal to pi and greater than or equal to 0, then the absolute value of the magnitude, or the length of A cross B, the absolute value sign, equals to absolute value of A times by absolute value of B, and then over the length of A and length of B times by sine of theta, like that. Alright, and now let's take a look at the proof of this theorem 2, and the proof is quite extensive, just very tedious, but pretty straightforward. So let's just jump right in. So from the definitions of the cross product and length of a vector, as in my earlier video, just basically the distance length formula. Yeah, so what we have now is, let's just write this down. So what I'm going to do is I'm going to take the square root of this cross product vector, and then define it using the length of the vector formula. So that's going to be right here. So the length of the A cross B, then square it, just so we're dealing with squares, is equal to, again, just Pythagoras theorem, essentially in 3 dimensions. So this is going to be, so this vector is going to be C. I just write it like here. This equals to, remember this one, this is going to be C1 term squared, the x term squared, and then the y, then the z. This is going to be C2 squared plus C3 squared, like that. And then to get the distance, you would square root everything and get rid of this. But anyway, so that's what we have there. And we know what these C1, C2, and C3 are. Those are just using the cross product. And that's going to be the C1 is going to be, well, it's going to be our A2, A3, if you remember that. And then it's going to be A3, this is A B2. A2, A B3, and then A3, B2. And then we're going to square this. And remember, this is the, that's just going to be right over here. This is A cross B. You have the first terms, A2, B3 minus A3, B2. In other words, this part right here. And yeah, so we just have this here. A2, A3 minus A3, A2. And then the next one's going to be negative A1. Negative bracket A1, A3 minus A3, A1, and so on. Alright, let's just continue back here. And, but here again, we're going to be squaring it, so it doesn't really change anything. Yeah, so whether you put plus or minus, it's going to get rid of it. But I'm going to do is I'm going to put a plus here, and then put this inside. Remember, it's going to be our negative A1, B3, but I'm going to switch it all up, and just write this as A3, B1 minus A1, B3. Again, just multiply that negative inside. Same thing as here. So negative inside here. So negative, we'll have this positive A3, B1 minus A1, B3 once you get rid of this negative there. But anyways, it doesn't change much because you're squaring it. So we have squared like that. Alright, so now the next one is the C3. And that's, remember that, this is going to be their A1, B2, and then minus... this is going to be A2, B1, and then square this again. And now we're just going to FOIL out or expand all of these squares. So let's do the first one here. So this term is going to be multiplied by itself, then multiplied by this one. So in other words, we're going to have an A2 squared, B3 squared, and then minus here, and let's write these all in order. So A2, A3, and then we'll have a B2, B3. Like that, put this all in order. And the next one's going to be this multiplied by this, and then itself. In other words, we're going to have the exact same setup as this. And so in other words, we just add them up, so we'll have a negative. We just add a 2 there. It'll be 2 of those, and then this one multiplied by itself. And the negative becomes positive. This will be a plus A3 squared b2 squared. And now the next one, I'm going to put this, we're going to FOIL out the middle one, but I'm going to write this underneath just so it's all in one stacked up column. It's easy to simplify. So just write this out. So just multiply by this, and then multiply by that. In other words, we get plus a3 squared b1 squared minus, now we're going to have a1, a3, and then b1, b3. And then next setup is this multiplied by this and itself. In other words, we're going to have the exact same this, add a 2. And then plus, the negatives cancel, a1 squared, b3 squared. And now the next one is, we're going to go over here. This times this, and this times this. This is going to be, this is going to be a1 squared, then b2 squared, and the next one, these multiply each other. Just write these all in order. a1, a2, b1, b2. And now the next setup is this multiplied by this, and then this multiplied by itself. In other words, we're going to get the same one here. Put a 2, and then plus right here. This the negatives cancel. So a2 squared, and then b1 squared, like that. Yeah, so now we have two very interesting setups. One of them is these square terms, and the other one is these -2 terms like that. So what I'm going to do is I'm going to separate all of them and write these in order where the A1, A1 to A3 and B1 to B3, etc. So the smallest one we have is this A1 the A1 is the smallest one there. So A1 squared, B2 squared, like that. Now the next one's going to be, well, the next setup always use the A1 as the smallest, basically go from small number to big number. So A1, B3. Just write this in order just to find a pattern. A1 squared, B3 squared. And the next one, there's no more ones. We'll look at the 2. So the 2 is this one right here. And that is, well, just plus A2 squared, B1 squared. And the next 2 is over here. A2 with 3, B3 there. Plus A2 squared, B3 squared. And the next one is just A3, B1, A3, B2. Plus A3 squared, B1 squared. And then plus A3 squared, B2 squared, like that. Alright, so now that we have that, and I'm going to do this here. I'm going to factor out the negative, but keep the 2's there, because they're very interesting. So we're going to have a negative, and then keep them all there, make it from the smallest to biggest, so A1, A2. Alright, so I have a 2, A1, A2, get rid of all these lines. Whoops. This line, this line, this line. So we'll get this one first. A1, A2, B1, B2. And then the next one's going to be plus this one right here, A1, A3. A1, A3, B1, B3. And then the next one is this one right here. And then just get rid of all these. This is going to be plus 2, A2, A3, B2, B3. And now we could find some interesting patterns. And now the interesting patterns here is not what's shown, but it's what is not shown. And this is pretty next level proof here. And what we'll do is, if you take a look at this one right here and the bottom one, this part right here in the bottom, there's some cancellation going on when we take a look at this. So I'm going to write here first. Note what happens when we have this kind. So we have this A1, B2, but there's no A1 or B1. There's no A3, B3, etc. or A2, B2, and those ones. That's because they would cancel, and we write them in a way that we're going to show right now. But first, I'm going to do is note that when we have this setup here, let's say we had an A1 squared plus a B1 squared, just so we have all these multiplications. So A1 squared, B2 squared, and so on. So if we have A1 squared plus B1, A1 plus A2 squared. And then the next one plus A3 squared. And then multiply this out by B1 squared plus B2 squared plus B3 squared. This equals 2. Yeah, so this whole thing equals 2. And I'll write this actually. Let's make it some neater here. Move it here. And write this as this equals 2. This is b3 squared. So again, FOIL this out. a1 goes over here and a1 go across like that. This is going to be, the top's going to be a1 squared, b1 squared. Notice that there's no more a1 or b1 squared. I'm going to circle the ones that are not inside this setup here. And the ones not inside is this one here. There's no, with the same numbers, a1 and b1. The next one's going to be this multiplied by this over here, b2 squared. So a1 squared, b2 squared. And that is this right here. So we have that. But we don't have this one here. And the next one's going to be multiplied out. It's going to be a1 squared, b3 squared. So we have all the ones. We have b3. It's not a cube. It's squared. Squared. And then what you'll see is this right here. Yeah, this one right here shows up here. So all the ones that don't have the same subscript are showing up there. Now we'll do the next setup. Next setup is this right here. This multiplied by this, and then this. So the first one's going to be plus a1, a2 b1 squared, a2 squared, b2 squared, and then the next one's going to be the same subscript. So a2 b2. A2, B2, and yeah, this one's A2, B1, not B2, and then the next one's going to be A2 squared, B3 squared multiplied by this one. And notice again, this A2 squared B1 shows up here. This one here, A2 squared B3 shows up here. So they all show up, but the ones that don't is the one that subscript's the same. So I'm going to circle this right here. I'm going to circle that. This one and this one aren't there. A2 squared, B2 squared do not show up in this top row. And let's do one more, is multiply this by this by this and add them up. This equals 2 plus, we'll have an A3 squared, B1 squared, and then plus, and you can see the pattern. Very interesting. A3 squared, B2 squared, and the next one is A3 squared, B3 squared again. These ones show up A3B1, 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 A3B2, A3B2. So those all show up. This one A2B3 is over here and so on. A2B1 here and here. And again, just to double check that. And then lastly, there is no A3B3 inside there. I'm going to put a plus here. And I'm going to circle the ones that are not inside. Alright, so now that we have this, this is pretty much this entire thing, but there's these extra terms. And now we have this part right here. So notice what we have here, this 2a, a1, a2, b1, b2. And these ones arise, remember when you have these squared, when you're multiplying the ones that are not itself, you're going to eventually have this 2 there. So this gives us the idea of, well, let's just try to square these ones all together. So we'll have this a1, b1, and then a2, and then plus a2, b2, plus a3, b3 all squared. Yeah, in other words, so first note that, and again, this is why this proof is a bit next level. We'll take, if I didn't have the solution, well, then even the solution, the calculus book doesn't actually explain this. They just go jump straight ahead, and I just had to, then I had to go and obviously reason that this is what they're doing. But if I had to do this from scratch, it might take a few days to figure out how they do this. But anyway, so now another thing. So we have this first, and now the next one is and. Note that to get this set up here. So what we're gonna do here is I'm gonna write a1 b1 plus a2 b2 plus a3 b3 squared. And again, the reason is when you're squaring these, when you're multiplying the not itself, you're going to eventually get something like this, where you have a1, b1, a1, b1, and then a2, b2, etc. Multiplied by there, and so on with these a3s. So now we're going to square this. So this equals to, well, this multiplied by itself, and then multiplied by this, multiplied by that. This is going to be, well, a1 squared, b1 squared. And I'm going to circle the ones not inside. And that's this one here. Remember, this matches up. That matches up, and it's not inside this part right here. Next setup is A1 and then A2, B2. So we're going to write these in order, A1, A2, and then we'll have a B1, B2. Let's put these in order just so it matches up with this. So we have this part right here. That's one of them. Next setup is this is going to multiply by this A3 plus A1, A1, yeah, A3, B1, B3. Yeah, A1, B1. Yeah, so then, and that's going to match up with this right here. A1, A3, B1, B3. One of them, not two of them. But then we're going to get that eventually. So now we're going to multiply this by it, this one, by itself, and then by this one. So that's going to be plus A1, A2, B1, B2. And that's going to be the same as this one. You're going to add these up. It's going to be 2. Those add up and so on. So we'll do that in a bit. And then the next setup is going to be, well, this by itself is going to be A2 squared, B2 squared. So notice that. So this is not inside any of them, but it matches up with this. Next one's going to be, well, A2, A3. A2, A3, and then B2, B3. And that matches up, well, it's going to match up with a different one. That's going to be now the next setup here. But again, also notice A2, A3, B2, B3. That's right here, A2, A3, A2, A3, B2, B3. And let's do the next setup is this one, multiplied by this, then itself. So that's going to be plus A1, A3, B1, B3, which is this. So those add up to be 2 of them. And the next setup is A2, A3, and then B2, B3. So that's, again, this multiplied by this, and these ones add up to 2. Yeah, so 2 of those, these exact same ones. And then this multiplied by itself is going to be plus A3, B3, squared, squared. So this is not anywhere inside here, but it shows up here. So then, in other words, all these terms, yeah, all these terms are inside here except these ones, and these ones actually can cancel. But let's just add these up. So this adds up with this with this, and this with this. So this equals 2. This equals 2, 2 A1, A2, B1, B2, plus this one right here, 2 A1, A3, B1, B3, plus 2, and then this right here, A2, A3, B2, B3. And then likewise, we'll just add these up there. And then over here, it's going to be A1 squared, B1 squared, plus A2 squared, plus B2 squared, plus A3 squared, B3 squared. So in other words, we have this part right here, and this part is when we combine these two, but then these all cancel. So thus, I'll put these all together. Thus, we get, and let's write this all down, thus A cross B squared is equal to, let's go A cross B is equal to, well, this is a C squared, like that. Yeah, I forgot to add that square there, but anyways, we have a square there. Everything's squared. This becomes C squared, like that. And this equals 2, and it's going to be, what I'm going to write down is this part right here. So this is A1. Yeah, I'll write these all out. I'm going to write this out like this. A1, A2, yeah, so let's write these out. A1 squared plus A2 squared plus A3 squared times by B1 squared plus B2 squared plus B3 squared minus this one here. So now it's going to do minus, and it's going to be minus, but actually to save some space, I'm going to remove the C squared, but a good thing we caught that that mistake. We had forgot the square, and then it's going to be minus, and then this part right here, all squared. Let's get rid of this thingy. Minus A1, B1 plus A2, B2 plus A3, B3 squared. Because remember, so when you have this minus this one, all of these cancel. And we're just going to be left with this giant -2, etc. there, which is just this whole setup here. And all of these extra terms. And then these ones are all gone. So these just all cancel. which is quite fascinating. All right, so that's what we have there. That's what this equals. And now, well, let's shift this over. Get some more room. Like this. And now, well, what do we have here? This right here is equal to, this is just the distance formula squared of a1, of a vector squared, like that. Yeah, that's just distance formula, or the length of it. Remember, a1 squared plus plus a2 squared plus a3 squared. So those are all the ones, you just square them, similar to the c1 squared plus c2 squared, etc. So you all those up, and then this one here is the b vector distance squared, or the length there. And now this part right here, inside here, this is just a dot product. Yeah, inside this thing is just a1, b1, all the terms, and add them up. In other words, this is just a dot b, like that. So what we get is, well, this whole thing is equal to, let's put an arrow, so I'll just leave it like that. This equals to a vector, the distance vector, a squared, and then like this, b like this, squared, then minus, then this is all squared 2, so of an a dot b vectors, yeah, dot product squared, like that. Like that. And now if you recall the dot product from our earlier video, this dot product is equal to, this one is just equal to, well, a vector, the distance of a, so the length of a, times length of b, and then cosine theta. That's just a dot product there, in with a trig format there, or geometric interpretation or definition. And then this just then write this whole setup, and now you're squaring it. So this equals, let's put an arrow like that, or just leave the arrow so that it equals that. So now this equals to a length of a squared times length of b vector squared minus, and then this is all squared, so we're gonna have to square everything. A squared length, yeah, a length of a squared, length of b squared, and then cosine squared theta. And now what we could do is, well, factor out this a squared b squared length. This becomes a squared b squared, then factor that out, becomes 1 minus cosine squared theta. And again, recall the Pythagorean trigonometric identity. Recall that you have 1 equals to sine squared theta plus cosine squared theta. So in other words, move this over to this side, you're going to get this sine squared. So 1 minus cosine squared theta equals to sine squared theta. So this whole setup equals to, and I'll put this all here. So we'll have, a cross b squared is equal to a length of a squared times length of b squared, and then we're going to have, yeah, here, sine squared theta, like that. And now we're going to recall the sine function. So we're now recall just the sine. So recall that it's positive for thetas between 0 and pi. So recall, if you have here, this is theta, this is y, like that. This is positive from pi, this is 0, and this is sine theta graph. So in other words, we have here's positive, so that means square root of sine theta, square root of sine squared, of sine squared theta is equal to sine squared, because it's going to be, yeah, so you cancel this out, and it's going to be, it's just going to be equal to sine squared, because it's always positive. So because remember, when you ever have this squared there, yeah, the squared makes the sign, if it's negative or positive, makes it positive, and then the square root just becomes a sine. But this case, because it's always positive, you could just square it, and you don't need to worry about negative sign. Yeah, so I'll just put sine squared equals the square root of sine squared is equal to sine squared because, and then write because sine theta is greater than or equal to 0 for, let's put the 4, I'll just shift everything over to the left, for theta is less than or equal to pi, or 180 degrees, and greater than or equal to 0. Alright, so thus we have, put it like this, and drag this out here. So thus, we got square root of this whole, square root this whole thing, square root of the dot of the cross product A cross B squared equals to square root of this whole setup here. Length of A squared, length of B squared, and sine squared. Like that. This equals to, yeah, this all of this cancels, so we're going to be left with A cross B equals 2, and all these squares cancel. We're just going to be left with A, length of A times length of B times sine theta. And there is our proof of theorem 2. It's a pretty extensive proof. I had to go a bit outside the box using the FOIL method of algebra FOIL method of those functions. And yeah, let's go scroll all the way back up to the theorem that we're actually proving. There it is. A cross B, the length of it equals to length of A times length of B times sine theta, for theta is between 0 and pi, or 0 and 180 degrees. Alright, so now that we got the proof there, let's continue marching further. So since a vector is completely determined by its magnitude and direction, we can now say that the cross product A cross B is the vector that is perpendicular to both A and B, whose orientation is determined by the right-hand rule, and whose length is the length of A times length of B times sine theta. In fact, that is exactly how physicists right here define A cross B. Very interesting. So they define it this way as opposed to mathematics. We proved it this way. So anyways, going further, so corollary or a theorem that follows another one. So two non-zero vectors A and B are parallel if and only if their cross products equals to 0. So A cross B equals to 0, or the 0 vector, like that. And again, this corresponds to this sign right here, because so when sine is 0 or sine is pi or 180 degrees, that becomes 0, so this whole thing becomes 0, and in other words, it has to be parallel, and we will illustrate that soon. And yeah, here we'll look at the proof of this. So two non-zero vectors A and B are parallel if and only if theta is equal to 0 or pi radians, or 180 degrees. In either case, sine theta is equal to 0, so A cross B is equal to 0, and therefore or the distance. This is the distance. The distance equals 0, and therefore A cross B is equal to 0. So in other words, this right here has to equal 0. So let's write this here. I'll just first of all graph this out. If you have vector A like this, say you have A, and then let's say you have A, and then you have a vector B. If it's parallel, this angle is, well, this theta is, I'll put the theta like this. Theta is equal to 0. This is B, so it's parallel. And but if you otherwise, the other way to get it parallel is if it goes here, which is a perfect 90 degrees. So let's say you have, instead of that, say you had B over here. This is pi. This theta is equal to pi radians, like that. So in either case, let's put this, scroll back here. Yeah, 0. Yeah, so this basically 0 there. So what we get is the distance A cross B is equal to length of A times length of B, and then sine 0, I'll put a 0, or pi. In either way, it's going to be equal to 0. 0 or pi equals to, well, yeah, this whole thing becomes 0. It just becomes, made for completeness, length of A times length of B times 0, which equals to 0. So then, if the length is 0, the cross product is going to be all 0. The only way you can get a length of 0 of a cross product of a vector is if the vector is a 0 vector. You can't have you can't have it pointing out somewhere and then having a length not 0. Can't do that. I mean, you can't have it pointing out somewhere and the length equals 0. You can't do that. 0 means not pointing anywhere. This equals to 0. The 0 vector. So yes, and that's a corollary from this theorem here. So if they're parallel like this, because remember this parallel, this B is parallel with this. I'll make this a bit better, like that. This is parallel as well. Yeah, these are all parallel together. All right, so now let's continue further, and now let's look at the geometric characterization of A cross B. Actually, not A cross B, more like Theorem 2. So geometric characterization of Theorem 2, which is this right here. It's just this formula right here. So, yeah, so if we write these lengths out, and then also this angle, remember sine angle, this would look like this. Let's just draw this out. Let's say you had A as a vector pointing out, I'll point it out like this. Here's a vector A. There's A, like that. Let's say you had B pointing out like this. This is B. And then the angle, theta, is between here and here. Goes like that. So, and then the geometric interpretation of, well, you have the length, like this. Okay, so you have the length here is the A length. Just leave it like that. But now this length right here, this is equal to, well, just using Pythagorean theorem, the opposite over adjacent is going to be sine. So in other words, sine theta equals to this, opposite OP over hypotenuse, I mean. In other words, and then you can move this over, and then you're going to have this part right here, the opposite. Which is just going to be, well, we all know this is just going to be the length of of B times by sine theta. Like that. And I'll just, I'll put that here. So, recall Pythagorean theorem. Or actually, it's pretty straightforward. I'll just put this recall. You'll have sine theta equals to opposite over hypotenuse, in this case, B. Move it over like that, and then you get this. All right, so that's what we have there. And here, just move it downwards there. And now, so we have that length there. And now if we draw this out like this, draw a perfect parallelogram like this. Or not exactly like that. Make it like this, and this is all parallel. Parallel. Yeah, just make it parallel. It's pretty straightforward. It's parallel. And so that this whole area here, and this whole length here, this times by this height there, that's just the area of this parallelogram. And again, this is just this exactly, you could view it as a rectangle that's shifted. Just a rectangle that's shifted. So in other words, a times this. A times the height, length times height is equal to the area of the virtual rectangle, or the stretched rectangle, or just the tilted rectangle or parallelogram over there. All right, here I just move things over, and now if continuing further, so if A and B vectors are represented by directed line segments with the same initial point as I just drew here, then they determine a parallelogram with base right here. The length is the length of this vector A. Altitude, or the height here, of B sine theta, and area is just going to be, well, area is just going to be like this, equals to the length A times by the length B sine theta. So basically, length times height of this this twisted rectangle, like that. And this is just equal to, well, again, this is just the Theorem 2. So that's just Theorem 2. So this length of A times length of B times sine theta. And this just equals to the length of the cross product, AB. So you can see the length of the cross product, the geometric interpretation, is the area of this parallelogram, which is absolutely fascinating. All right, let's erase that. And that is what we have. Yeah, so thus we have the following way of interpreting the magnitude of a cross product. And that is, the length of the cross product A cross B is equal to the area of the parallelogram determined by A and b. So you have a parallelogram like this. Draw this across where these are parallel, 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 like that. There's a parallelogram. All right, and now this brings us to example 3. So this one states, find a vector perpendicular to the plane that passes through the points P, 1, 4, 6, Q, -2, 5, -1, and R, 1, -1, and 1. Let's take a look at the solution. So the vector PQ, so look at PQ, cross product, get the vector PQ cross PR is perpendicular to both PQ and PR and is therefore perpendicular to the plane through PQ and R. So again, we were asked to find a cross product passes through these right here, or vector, or we're asked to find a vector that passes through these, and one way is obviously the cross product. And just to illustrate here, so we have the points P1, P1, 4, 6, PQ and R. Let's just graph these out. Let's just illustrate this in 3D, just to grasp it. That's what I had to do initially, just to grasp what they're talking about. Let's say we had Y here, and there's a Z. There's the x-axis. And let's draw the point P. P is 1, 4, 6. So we have 1, and then goes up 1, 2, 3, 4, and then 6. So it goes 1, 2, 3, 4, 5, 6. Somewhere across there, and it's going to go up like this. Yeah, it's going to be somewhere across here. Just try that there. Like this, and then dot, 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 like that. This is P. Alright, so that's P, and let's look at Q. Q is -2, 5, and 1. So we go with -2. It goes like this. 1, 2. And that's negative, and it goes forward 5. This is 5. This is 4. It goes over across here, like that, and then goes -1. It goes down 1, and yes, it's going to go down 1. Let's put it here, like that. So it's going to be somewhere here is Q, like that. Next setup is R is 1, -1, and 1. All right, so R is 1, and then it goes backwards 1. Like that. Like this. And let's fix this better. Make this better. Like that. Okay, and it goes backwards 1. And it goes up 1. So it goes like this. So it's going to be here. This is PQR. Like that. Alright, so now what I'm going to do is, well, we want the vectors PQ and PR. So what I'm going to do is, I'm going to shift this, I'm going to write this in red. PQ is like this. So if you have the vector PQ, this is PQ like that. Or actually, well, actually, this isn't typically called PQ, but this is just a vector like this. And vector, this is going to be the PR placement there. But then what we're going to do is we're going to shift this over here. If we recall from our earlier video, if we shift this here and make it exactly parallel to that, exactly this setup here, this one here, this is going to be our PQ. So the PQ vector, or position vector, starting from the origin, just so we can do some calculations with it. The next one's going to be set up here, parallel with this one. This is our PR, like that. So just recall from that earlier video on this. Alright, so now let's continue on this, and again, this brings us our attention to my earlier video. So recall from my earlier video on vectors that the position vector A of the point P can be written as follows. And this is again when we're given 2 points and it's parallel to it. So if you have given the points A, which is x1, x2, xy, and z, or x1, y1, z1, etc. In this case, here's our A. And B, which is x2, y2, z2. So in this case, yeah, so this is our B right here. So there's A and there's B. The vector A with representation AB is going to be given by this A vector. It's actually going to be over here. This equals to AB, like that. And this equals to the difference between these two. So x2 minus x1, y2 minus y1. And then if you have the B right here, if you subtract these, x plus a1 and then subtracted by this x, you're just going to be left with this a1, a2, a3, and you're going to be left with here. So in other words, we get a parallel, we just shift this over to here, and this is the position vector of this point P, which is exactly just AB. So this A equals to AB. So that's exactly what we're doing here. So we have to move this down here and then take the dot product, the cross product of that. All right, so now we have that. Let's continue further. So thus from the above formula, we know that the position vectors PQ and PR are, and well, let's just write these down, and let's just write these down here. So P146, negative 25, negative 1, and so on. Let's just write them down here so we don't need to keep scrolling up. So P is the position, the point P is 146, and then Q, put a comma there. Q is negative 2, 5, 1. Negative 1. Negative 2, 5, and then this is negative 1. Like that. And then the next one is R. R was, if I remember, 1, negative 1, and 1. And that's just going to be 1, negative 1, and 1. Negative 2, 5, negative 1, and 1, 4, 6. So we have all this. So then this means that position vector PQ from the origin, when we shift it over there, is going to equal to, this equals to, and again, using this formula, we just subtract them. There's just a difference there, and then we could write them starting from the origin. So PQ, we subtract negative 2, and we could write this in, the calculus book just writes this in the IJK notation, or the standard basis vector notation. So what we could do here is a negative 2 minus 1 I, and then plus, we're going to have 5 minus 4. So 5, the Q there, 5 minus 4, J. Like that. And the next one's going to be R. I mean, not R. The next one's going to be this Z components. Negative 1 minus 6. Negative 1 minus 6. K. Like that. This equals 2. Negative 3I, like that, plus J, because 5 minus 4 is 1. Next one is negative 1 minus 6 is 7. Negative 7. Negative 7K, like that. So that is our PQ. Now we got to get the other point PR, and PR is going to be, again, it's P to the R. We just shift this, write the position vector from the origin. There, and these are just parallels. So if you get one that's perpendicular to this, it's going to be perpendicular to this. In other words, you just stick it out. So if you have a vector sticking out like that, the cross product crosses both of them. All right, let's continue further, and the next one is PR. PR, like that. This equals 2, so PR, so we're going to go 1 minus 1, 1 minus 1, and this is going to be I, plus the J1 is negative 1 minus 4. J, and then the next one is going to be 1 minus 6. 1 minus 6, K. So this equals 2, well, we have, this is 0, so we could get rid of that. Next one's negative 1 minus 4 is negative 5. J, next one is going to be 1 minus 6 is negative 5. K, like that. So we have all this. And let's just box it out. Next step is, well, we just take the cross product. Alright, so now that we have this, and we compute the cross product of these vectors. So in other words, we get this PQ, like that, cross PR vectors. This equals 2, and write this in the determinant format. We have the IJK, so we have I here, J here, and then K here, like that. And then the I, the first one's going to be negative 3, 1, negative 7. Negative 3, 1, negative 7. Next setup is going to be as well 0, and then negative 5, negative 5. And now we could just solve all this. Well, remember, the first part is going to be, we look at this, and then we just turn this, this multiplied by this. Let's do it all in one go, instead of writing it all out. This multiplied by this, and then subtract by this. All right, so let's cross these out. And we're going to get 1 minus negative 5. 1 times negative 5 is going to be negative 5. Minus, this one's going to be positive. Yeah, negative 7 times negative 5 is going to be plus 35. So just minus 35 like that. Next setup is, well, this and this. So we get negative 3 times negative 5. So we get, and this is going to be a minus. So minus negative 3 times negative 5 is going to be plus 15 minus negative 7 times 0, 0. This is j, like that. And let's erase this and this. Next setup is this and this, like that. This is going to be plus, and then so negative 3 times negative 5 is again going to be 15. And then minus 1 minus 0, 0. Like that, and we can just get rid of this. Alright, now this equals to, well, negative 40 I minus 15 j plus 15 k, like that. And that is our vector. And this is perpendicular to that plane. Alright, so let's continue further. So yeah, so the vector negative 40, negative 15, and positive 15 is perpendicular to the given plane. And any non-zero scalar multiple of this vector, such as negative 8, negative 3, and 3 is also perpendicular to the plane. In other words, a scalar multiple, you're going to make it smaller, shrink, smaller, bigger. It's always going to be perpendicular to that. And again, we just shifted this this plane over to this side here. And if you get through, if it's one perpendicular to it, it's also perpendicular to this one too. And you scalar multiple all the way through it. Anyways, just erase this. One more. And I think I got rid of it. Alright, we got rid of all those. And let's continue further. And also just calculation check here. This is a scalar multiple. So negative 40 divided by negative 8 is equal to 5. So negative 15 divided by negative 3 is equal to 5. And then 15 divided by 3 is 5. So in other words, this is all dividing these out by 5. So yeah, scalar multiple of 1 over 5. Anyways, continue further. So example 4. Find the area of the triangle with vertices P as 1, 4, 6, Q is negative 2, 5, negative 1, and R is 1, negative 1, 1. In other words, it says find the triangle, find the area of the triangle of these vertices, and that's exactly this setup here. These are the same coordinates, and it's just saying find this triangle. As opposed to, well, you guessed it, the parallelogram. So they're saying as opposed to that, so you're going to have to go find the area of the parallelogram, divide by 2. Remember, that's just parallelogram is just two triangles. All right. So let's look at the solution. So in the example, we computed PQ cross PR vectors equal to negative 40, negative 15, and 15. The area of the parallelogram with adjacent sides PQ and PR is the length of this cross product. Remember, that's the length of the parallelogram. So in other words, we just take the length, and we know the length formula. That this is the parallelogram. Then we're going to have to divide by 2 in a bit. So PQ cross PR, the length or absolute value is equal to square root, and using the length formula is just going to be, well, negative 40 squared plus negative 15 squared plus 15 squared, like that. And if you plug this into the calculator, you're going to get a 5 square root 82. And before we go further, let's do a quick calculation check. So here's my OneNote program has a built-in calculator. So we go negative 40 squared plus negative 15 squared plus 15 squared equals to this. Let's put a equals space. So 2050. And now what we'll do is, well, 2050 divided by 25, that equals actually 82. You see, it's a factor of 25. So in other words, 2050 square root, or the power of 1/2, is just going to equal to 25 times 82, which equals to, remember we have 25 times 82 is equal to 2050. And then this is all square root. And then in other words, and if you square root 25, that's just 5 times 5, so that equals to 5 times square root 82. So yes, 5 times square root of 82, like that. Is what we have. Write it better, 8, 2. And the area of the triangle PQR is half the area of this parallelogram, that is 5 divided by 2 times square root of 82, or 82 to the power of 1/2. So in other words, if we have PQ like this and PR, and then if this is a parallelogram like that, double parallel to this, then the area is going to be 1/2 that. So half and half, and then we get a triangle. And that was we were asked to get PQR triangle there. So find the area of the triangle, the vertices PQR, etc. Alright, so now let's continue further, and this time look at properties of the cross product. So if we apply theorems 1 and 2 to the standard basis vectors I, j, and k using theta equals pi over 2 and the right hand rule, we obtain, and we're going to obtain a bunch of formulas for this. And remember, theorems 1 and 2, so theorem 1 is just the orthogonality, or to pronounce it better, orthogonality principle. So theorem 2 is the distance one, which is using that parallelogram AB sine theta. And then theorem 1 is the vector A cross B is orthogonal to AB, A and B, or perpendicular to it. So let's use those two theorems and then find some properties of the IJK basis vector. So we have the property 1. So we have the theorem 1, A cross B is perpendicular. Let's put this like this. Perpendicular to let's put a better one here. To A and B. Then theorem 2 is that the length of A cross B is the parallelogram equals to A cross B. Length of A times length of B, and then sine. In this case, we're going to be dealing with pi over 2 or 90 degrees because basis vectors are all separated by 90 degrees, so pi over 2. And pi over 2, the sine pi over 2 is just equal to 1. So this just equals to A cross B. And then this is going to be, this is equal to all 1 because these are all the standard basis vectors I, j, k all have lengths 1. So 1 times 1 times 1 equals to 1. And this is equals to 1 since, and I'll put since, I'll put it actually here, since, I'll put it here, so since I, length of I, the standard basis equals to length of j, that's better, j equals length of k, like that, which equals to 1. Alright, so since they all equal to 1, and yeah, so you're just going to have a 1 times 1 equals to 1, and this sine pi over 2 is equals to 1, and again, you can recall that. I'll go back to our drawing here of the sine one. This length is 1. This is at pi over 2. Like that. So it's pi over 2 is right there, 90 degrees, and that sine pi over 2 is equal to 1. Alright. And yeah, that's what we have. And now let's draw our standard basis vectors like here. So we have, I'll write it like this, make it a bit smaller. So this is our y axis, this is our z, this is our x. Now this is going to be I, is the unit length of I there. And then the unit one of the j is right here. This is j. And then k is above here. K. And they're all, they're all, put it like this. Where should I put this? Oh, right here, just fix that up here. So I put the k like down there. I should put the k up higher so it doesn't get any confusion. And this is the j right there. Alright, so now let's do the properties. So I cross j. And using the right hand rule. So I cross j, remember the angle is going to be like this, using the right hand rule. Right hand's like this, so if it curls inwards this way, the thumb's going to be pointing up. Yeah, so from I, this is going to be like this. And again, all these angles, let's put another thing here. All these angles are pi over 2. So theta is equal to pi over 2, and theta is equal to pi over 2. Theta equals to pi over 2, and so on. And another one here, theta is equal to pi over 2. From all these angles, these are all 90 degrees. And so on. I'll just, yeah, it's pretty straightforward. So everything's 90 degrees, all of these. Or pi over 2 radians. Alright, so I cross j, using the right hand rule, is equal to k. Like that. And now if we go j cross k, this angle's like this. Right angle, the thumb's going to stick out this way. If you just use your right hand. So you're going to get j cross k is equal to I. Now the next one is k cross I, and then using right hand rule is going to be pointing to j. K cross I equals to j. You can use a cross product with the actual unit terms of it, like 1, 0, 0, and 0, 1, 0, and 0, 0, 1. And you'll get the same thing. Now the next setup is, notice what happens here. Now instead of going here, we go backwards. We'll go j to here. So then, in other words, you have to put your thumb downwards, because you're going with right hand, using the right hand rule. So you'll have j cross I equals to negative k, because the right hand rule points downwards. Now the next one is k cross j. K cross j is going to be this way. You're going backwards, and using right hand rule, it's going to be pointing this way, negative I. So notice how it always goes negative. Negative I, like that. And then the last one, I cross k. So I cross k, you're going to go from here to here, and if you point your arrows there, it's going to go backwards. Your thumb's going to be sticking out the negative side of j. Equals to negative j. So these are the properties of the standard, using the standard basis vectors. Alright, so now from this, observe that when you flip around the cross product directions, you don't get the same answer. So in other words, observe that I cross j, for example, so I cross j, this one here, is not equal to this. So I cross j is not equal to j cross I, like that. Yeah, so this property, because it doesn't have it, thus the cross product is said to be not commutative or commutative. Yeah, so you can't just rearrange it and do that. And note also that if you had something like this, I cross, and then bracket I cross j, this equals to, all of you know the properties, I cross j is equal to k. This is the same thing as writing using the brackets first, cross k. And then I cross k is right here, is equal to negative j. Negative j. But we have, well, if instead of doing this way, if you switched up the brackets here and here, like this, instead of that, you'll had I'll put a but like this, so I cross I, this, then cross j. This equals to, well, I cross I, we already showed that a cross a is equal to 0. It's just the same thing. Yeah, I think I was in the example 2 or example 1. Let's go scroll up. Where's that example? It's right over. Yeah, right over here, example 2. So a cross a is equal to 0 for any vector in the set V3 or vectors in 3 dimensions. All right, going back. to this. So we have this. So in other words, this means this is 0 vector cross j, and 0 vector cross anything 0. I mean, any other vector is going to be always 0. So in other words, these don't equal each other. Yeah, so then these do not equal. So I'll just leave it like that. Those don't equal. Yeah, so this is said to be, well, this is considered as, so the associative law for multiplication does not usually hold. That is in general. So in general, this isn't the case for cross products. A cross B bracket cross C is typically not equal to A cross, A cross and then B cross C in brackets. Like that. Typically, you can't just flip things around like typical multiplication laws. Alright, so although these don't match up with typical multiplication laws, however, some of the usual laws of algebra do hold for cross products, and the following theorem summarizes the properties of vector products, and here is theorem 3. So if A, B, and C are vectors and then unbolded C is a scalar, then A cross B equals to negative B cross A. That's property 1, and again, that was similar to this right here. We switched it around, it all becomes negative. And then number 2 is C times A cross B, this is in the bracket, equals to C. You could take the C out of all of these cross products. Equals C times bracket A cross B, and this equals to A cross, and then C inside the bracket. C and B inside this bracket there. And then property 3 is A cross and then bracket B plus C. And then this equals to, well, you could multiply this out and expand it out just like multiplication. A cross B plus A cross C. And then property 4, A plus B, and then all of that cross C is equal to, again, expand this out from this side, A cross C plus B cross C, similar to the property 3. Then property 5 is A dot B cross C is equal to A cross B dot C. That's a very interesting property. And then A cross and then B cross C is equal to A dot C times B minus A dot B times C. That's interesting. So you write these in terms of dot products there. All right, and these properties can be proved by writing the vectors in terms of their components and using the definition of a cross product. So we give the proof of property 5 here and leave the remaining proofs as exercises at the end of this video, and I'll prove those later. So yeah, Calculus book didn't prove those. I had to go do them on my own. All right. Also because the solution manual wasn't giving me the answer. All right. So let's take a look at proof of property 5. And property 5 is right here. A dot B cross C equals A cross B dot C. That's a very interesting one. Let's just write it down. So A dot B cross C equals to, and it's going to be a, this equals to A cross B, and this is in brackets, dot C. Alright, so now that we have this, and let's write it out. Let's say first, let's say we have our vectors as typical. So if A vector is equal to, and has components A1, A2, A3, like this. And then the B vector, components B1, B2, B3, and then the C1 is over here, equals to, I'll put a bracket, C vector is equal to C1, C2, C3. Like that. Then, so if we have that, then what we get is, let's say the dot product now. I'll put it if, and then I'll just put it then right here. A dot B cross C, this equals to, and again, remember the dot product, we just multiply each term. So the first one would be A1, and then the first term of this B cross C, which is a vector. And we already know this, and if you memorize it, it's just going to be our B2, C3, minus, and then, so we always go 2, 3, then it goes 3, 2. 3, 2, C2. Yeah, B3, C2. Yeah, next one you could subtract, but I'm going to just add there and then flip around the direction of it. So we're going to have the A2, so this the second component, multiplied by the second component of this cross product. Remember, initially it's supposed to be A instead of actually B. Instead of going B, it's supposed to be negative B1 and then C3 minus B3 C1. I'm going to get rid of this negative, put a plus, make this plus, make this negative. So put this first. In other words, we get a B3 C1 minus B1 C3. Let's write it like that. And the next one is going to be the third component. It's going to be A3 multiplied by, well, we know this one, B1 C2 minus B2 C1. And now what we're going to do is multiply this all out, and then what we're going to do is we're going to take out, instead of this A1, A2, A3, we're going to take out the C's to make it look like this dot product. And let's just get rid of this out, multiply this out, so we get A1 and then A2 minus, well, actually forgot to put the C3 there, so it's C3 there. A1, A2, C3, and then minus, right here, A1, B3, C2, and the next one's going to be plus A2, B3, C1 minus A2, B1, C3, then plus A3, B1, C2 minus A3, A3, B2, C1, like that. And now what we're going to do is factor out all the similar ones, and we'll do the C1s first, C1s like that. This equals to, factor this out, and let's put that C on the other side, so we're going to have this A2B3 minus A3B2 C1. And now the next one is going to be, well, C3, or actually C2, 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 like that. Next one's going to be plus, this is going to be A3B1 minus A1, B3, C2, and then likewise, I'm just going to shift this over, make some room actually, shift this over, plus, and this is going to be, the next one's going to be the C3. So the C3 is going to be A1, B2 minus A2, B1, C3. All right, in other words, well, now we're back to our square one here, and this is just the cross product dot, and the cross product is all these bracket terms, exactly the same one, A3, B1, number this one is B3, C1, B1, C3 is A3, B1, A1, B3, etc. So this is A cross B, and then dot C, those are the C terms out there. So in other words, this equals to A cross B bracket dot C. So we just solved property 5. That's equals to this one. Yes, fascinating stuff. Alright, so now that we solved this, this brings our attention to triple product. So the product A dot B cross C in brackets that occurs in property 5 is called the scalar triple product of the vectors A, B, and C. And notice from property 5, from the property 5 proof, that we can write the scalar triple product as a determinant. So notice here we have this cross product, then we have this A1 times by A2, A3, etc. In other words, this is just a determinant. So we could write this as, in determinant form, A dot B in bracket B cross C is equal to, and this is just going to be A1, A2, A3, and then B1, B2, B3, and then C1, C2, C3, like that. Alright, going further, the geometric significance of the scalar triple product can be seen by considering the parallelepiped, and I'll show you the shape soon. It's basically a 3D rhombus determined by the vectors A, B, and C as shown in the figure below. So let's take a look at this figure, and then I'll explain what this all means. So let's say you have the vector goes like this is A. Then you have the vector B like this. And then you have the vector C like that. So that's a vector C. And then you have a parallelogram across like this. So there's a parallelogram. But then it's in 3D now. We have a 3D parallelogram like this. Matches up with this. And then it goes all the way across. Whoops. Like this. And then this goes across like that. And then goes like that. Alright, let's just now draw the inside like this. It's going to go something like this. And then this goes up like that. Alright, here I just quickly fixed up this parallelepiped. So it looks like something like that. And now if we draw the cross product of B and C, which is perpendicular to it, and go up somewhere like this. Let's say this is the cross product. This is B cross C. Like that, and the height here is gonna be h. So from here, let's put the like this. From here to here is gonna be h, and I'm gonna draw this angle theta like that. All right, and I'll just draw a dashed line across there. So that's the height of this parallelepiped, and that's this shape right here. Basically a 3D rhombus. So the area of the base of the parallelogram, of the base right here, is A, which again is parallelogram across here, like that. That is just B cross C. That's just the cross product of these two vectors. So if theta is the angle between A and the B cross C vector, then the height h is going to equal to, h. Yeah, then the height h equals to, well, the length a times cosine theta. In other words, adjacent over hypotenuse. So we'll have, yes, here's just a sine. Recall, you'll have adjacent. I'll just put a cosine theta equals 2. And if this is a right angle triangle, adjacent, which is h, over hypotenuse, which is absolute value of a, or the length of the a vector. We moved it over across to there. So let's put that here. So cosine, or recall, cosine theta equals to h over, like that. I'll just fix that up and then move this over to there, and you get our h value. And note that we must use the absolute value cosine instead of cos, in case cosine theta is greater than pi over 2. And I'll put this absolute value sign like that. And yeah, there's absolute value sign there. And that's because if you recall, cosine goes like this. Becomes negative past the pi over 2. Like that. Yeah, and here I'm just going to draw that out. So recall, because we didn't do one for cosine in this video, but I've done this many times before. Other videos. So it goes like this and that. So this is pi over 2. Theta, this is y, this is our cosine theta. Yeah, just fix that up, cosine theta, and this is plus, then becomes negative past this cosine pi, past the pi over 2 there. Oh, so then therefore the volume of the parallelepiped is, well, just going to be this area times by the height of it. And because it's all paralleled here, you could view it as just a giant, 3D rectangle, and the height there. And whenever you shift it, you're not changing anything. You could view this as just a perfect block of rectangular block, where you can have the height here, and then you just shift everything. So if you were to, or actually instead of this way, oops. Yeah, so if you were to straighten this all out and make it into a rectangular block, you would just have this shifted across here, just shift over everything, and it's just going to be height h. And this would be all parallel exactly like it. And yeah, so and then you could view it as basically having a rectangular block and then shifting it accordingly, and nothing actually changes. Yeah, so basically the area is going to, the volume is going to be this area times by this height. All right, let's continue further. So therefore, the volume of the parallelepiped is V equals to A times H, which equals to, well, cross product is the area of the base. B cross C, then the height is A times by cosine theta. Yeah, so we scroll up here, so there's the height H is equal to the length A times cosine theta. And so would you have this? And note, this is just a dot product. Yeah, so in other words, this is just a vector, length of vector, B cross C, and then times by length of this vector A, and then times cosine theta. That's just, again, dot. This is just literally the dot product. And what I'm doing is I'm going to switch these around, because these are just lengths. These are just basic multiplication of lengths. Switch them around so that we can write it in the form we're used to. So then we'll switch those around. We could write this as A. Length of A times by length of the cross product B cross C, and then cosine theta, absolute value. Again, this is dot product. This equals to A dot, then this vector. So this vector dot B cross C in bracket like that. And there's what we have. This is a triple product. So the triple product is a volume of the parallelepiped. All right, so thus we have proved the following formula. So formula of a parallelepiped. The formula of the parallelepiped determined by the vectors A, B, and C is the magnitude of their scalar triple product. That is, volume of the parallelepiped is equal to A dot, it's the length of the, or the magnitude, or the absolute size of the A dot B bracket B cross C. Like that. Absolutely fascinating stuff here. And here a note on it is, if we use the above formula and discover that the volume of the parallelepiped determined by A, B, and C is 0, then the vectors must lie in the same plane. That is, they are coplanar. And in other words, this A would be on the same plane, and there's no volume. It would just all be 0. Alright, now let's take a look at an example again. So example 5. Use the scalar triple product to show that the vectors A, which is 1, 4, negative 7, and B, which is 2, negative 1, 4, and C, which is 0, negative 9, and 18 are coplanar. In other words, all in the same plane. So let's take a look at the solution. We can use the determinant formula to compute their triple product. Or instead of saying can, or we just say we use the determinant formula to compute their scalar triple product. So in other words, again, remember, the scalar triple product is just A dot B cross C, and then you can write this in determinant formula. And then we know our A is going to be 1, 4, negative 7. And then our B is going to be 2, negative 1, 4. And then C is 0, negative 9. 18, plus 18. Let's double check. So we have 1, 4, negative 7, and then 2, negative 1, 4, and then 0, negative 9, 18. All right, now let's write this in this second order determinant form for completeness. This equals 2. Well, we get this 1 there, and then cross out everything there. So we put a 1 and write this down here. So it's going to be negative 1, 4, negative 9, and then 18. And then determine there. The next one's going to be, erase this. This is negative 4 because it's the middle one. Cross out. We get a 2, 4, 0, 18, like this. And then the next one is negative 7. And then we cross out, get a 2, negative 1, 0, negative 9, like this. Alright, so we have this. And then the next one is going to be, well, this times this, and then subtract by this, by that, multiplied. So anyways, so we get a 1 times it by negative 18, negative 1 times 18. Then minus, and then it becomes minus, negative becomes positive. So 9 times 4 is 36. Like that. Minus 4. Now we have a 2 times 18 is 36. Minus 4 times 0. 0. Like that. And then the next one is minus 7 times by negative 18. Then minus plus 0. We get minus negative 1 times 0 is 0. Like that. So we get that. And then let's see what we have here. Alright, so negative 18 plus 36, same thing as writing 36 minus 18, that's just 18. And then this one here, 4 plus 36, and then 36 is just 18 times 2. So what I'll do here is just get everything as a factor of 18. So then this could be 2 times 4 is 8. We'll have a minus 8 times 18, like this. Now the next one is, well, this negatives cancel, becomes plus 7 times by 18. So we have 18, so 18 minus 8 times 18 plus 7 times 18. In other words, this and this would be 8. So this one and this will be 8 times 18. Then minus 8 times 18. This equals to 0. Alright, so this is 0. So these are coplanar. They're all on the same plane because their triple product, their scalar triple product is 0. Alright, so therefore the volume of the parallel pipe determined by A, B, and C is 0. This means that A, B, and C are coplanar on the same plane, so there's no volume. Alright, it's very, very fascinating. So now let's continue further. So the product A cross B, cross and then bracket B cross C, that's property 6 right here. This one here, A cross and then B cross C. This is called, let's go here, this is that occurs in property 6 is called the vector triple product of A, B, and C. And property 6 will be used to derive Kepler's first law of planetary motion in my future video. So stay tuned for that. And its proof, its proof is, let's fix that up. Its proof is shown in exercise 5 at the end of this video. That's very fascinating. And now let's take a look at the next section, and that is on torque. So the idea of a cross product occurs often in physics. In particular, we consider a force F acting on a rigid body at a point given by a position vector r. So let's say you have a distance, here's the r, and then there's a force here. For instance, if we tighten a bolt by applying a force to a wrench, as in the figure below, we produce a turning effect, and the only part of it that actually generates that is the perpendicular one across here. In other words, the sine of the sine of that function, sine of the force there, going perpendicular to this direction there. All right, the torque tau, that's the Greek letter tau, relative to the origin is defined by the cross product of the position and force vectors. So the torque is equal to, so this torque is using the right hand rule, is going to be equal to, like this, the r position vector cross the force vector, like that. And then, so that is the turning effect there, and there's a position vector r, like that. Yeah, and this torque right here measures the tendency of the body to rotate about the origin. The larger the value, the more tendency it's rotating. The direction of the torque vector indicates the axis of rotation. So if it's pointing here, and then if you're doing right hand rule, this would be curling. Let's see how this would be. Yeah, this would be curling downwards. So right hand rule is this way. Your fingers are curling inwards this way, and your thumb is sticking out. Again, just using the right hand rule, like that. And then according to theorem 2, the magnitude of the torque vector is, and again the absolute value or the length or the distance, or just the magnitude of the torque is equal to the magnitude of the cross product of r cross f, which equals to the magnitude of both position vector and the force vector, and then sine theta. So there's that sine theta across here, like that, pointing downwards. Yes, and where this theta is again the angle where theta is the angle between the position and force vectors, like that. It's fascinating stuff. So now observe that the only component of F that can cause a rotation is the one perpendicular to R. So the only one, perpendicular to this. And that is, again, this force, the magnitude of the force times by sine theta. So it's only this component right here. Sine theta. It's perpendicular, like that. That's fascinating stuff here. Now let's continue further. So, and the magnitude of the torque is equal to the area of the parallelogram determined by R, position vector R, and the force vector F. Again, with the based on the cross product is just the parallelogram of those two vectors. And now let's take a look at example 6, the last example of this video. Then we'll do the exercises. So a bolt is tightened by applying a 40 Newton force to a 0.25 meter wrench, or 25 centimeters, as shown in the figure below. So here's you're tightening this one here, and you're doing you're doing clockwise. So your fingers are going inward. Yeah. So then the arrow is going to be going into the page, like straight down into the page. Like that is your thumb. So that's the torque is going into the page. Anyway, so there's the 0.25 is the R value, the length of the R. And then this is 40 newtons is the magnitude of the force. And there's the 75 degrees. And it says find the magnitude of the torque about the center of the bolt. So solution, let's go here. All right, let's move those over down here. So the magnitude of the torque vector is, well, we just use a cross product. So this is a tau. This is the torque, the magnitude of the torque, like this. So value sign is equal to magnitude of the cross product R cross F. This equals 2 using the theorem 2. So this is going to be length of R times by length of F times by sine of 75 degrees. And then if you plug this in, we'll also put everything in. So the distance is 0.25 meters. 0.25 meters. And then the force is 40 newtons. See that up here. So 0.25 meters, 40 newtons. This is going to be 40 newtons. And then sine 75. And then if you solve this again, this 0.25, that's just 1 over 4 times by 40. That's going to be 10 equals to 10 sine 75. Let's put this better. 75 degrees. And then if you and then now this equals 2. And this equals to, plugging in the calculator, gets 9.66 Newton meters. And I'll solve this. And I'll just box this. And then I'll do a calculation check. And here's a calculation check. So again, you can go 10 times sine 75 using my built-in calculator in OneNote. So press equal space. So, and this is automatically solves it with degrees. So you get 10 times sine 75 degrees is 9.659, etc. But you round up to 9.66. All right. So now going further. So if the bolt is right threaded, then the torque itself is, and this is, I think it's right threaded, just torquing with right hand rule. So righty tighty, like this. So if it's right hand is curling, if your fingers are curling in, you're going to be pointing into the page as your thumb. So if the bolt is right threaded, then the torque vector, remember the keywords, vector, not just the magnitude, this equals to, here's the torque vector, which equals to the magnitude of the torque times it by the vector going into the page n. We'll call this unit vector n. This would be writing as 9.66 newtons, and then this is times by unit vector n, like that. And again, where n is a unit vector directed down into the page, aka right hand rule with a thumb pointing into the page and fingers curling in a clockwise rotation. Again, remember, unit vector is just a magnitude 1, so you're not changing anything. All you're doing is stretching that unit vector to a magnitude that corresponds to the magnitude of the torque. It's fascinating stuff. So let's continue further and look at now exercises. We pretty much finished all these. And all the exercises I'm going to do is just prove the properties, prove property 1 of theorem 3, and basically we're going to prove all these properties. We already proved property 5, so we're going to do the rest. We're going to do 1, 2, 3, 4, and 5. And 6. 6 is going to be the 5th exercise. And that's the vector triple product. I think that's what it's called. Let's go see what it was called. Yeah, that's over here. So the vector triple product is property 6. Alright, let's just jump right in. Alright, so let's take a look at exercise 1. This says prove property 1 of theorem 3, and that's just A cross B equals to negative B cross A. So let's just write this out, and let's say we have our cross product here. So A cross B equals to, and again we know it's A2 B3, because again it's ingrained into my brain. The next one's going to be A3, B2, and then we're going to go, and I'll put it like this. I like this better than the IJK format. So we have these in these components. The next one's going to be A3, B1 minus, and then it's going to be minus, this is going to be A1, B3. Just the middle one, you switch up where the higher number is first, because there's a negative sign. And then next one's going to be, A1, B2 minus A2, B1, like that. And now what we're going to do is I'm going to take out a negative from this whole thing. I'm going to take a negative out, and then basically switch these around. If you take a negative out, factor a negative, this becomes negative, this becomes positive, because if you factor out negative from a negative, it becomes positive, and positive, factor out negative from a positive, becomes negative. So we get A3B2, or better yet, so you'll have A3B2, but I'm going to put the, I'm going to switch these around. So I'm going to put this one's positive, I'm going to put the B2 in front, so that we have the same matching subscripts too, but now we have a B there. Now we have A3 there. And then this is going to be now minus B3, A2. Next one's going to be, this is going to flip, and we're going to, this is going to be positive, but now we're going to put the B3 there, A1, minus, and then it's going to be B1, A3. Like that. And then next one's going to be B1, A2. This is positive, this part's positive, but we'll put the B in front. And then this is going to be negative, B2, A1. Like this. All right. And then now what we have, we took the negative all out here. So this equals negative. And well, we know all this. This is just we just switch these around where you have this is exactly the same thing here. Instead of A, we have a B. Instead of a B, we have an A. It's exactly the same thing. So in other words, we have B cross A. So this is just B cross A. So yeah, this is exactly it. It just equals negative of that. Let's check mark. We got it right. Alright, so now let's go further into exercise 2. And this one states proof property 2 of theorem 3. And that's this one right here, which is you have the scalar C times the vector A in bracket, and then cross B equals 2. You could take the scalar out and then times it by cross product A cross B. Equals 2, and you could also put the scalar inside here. So A cross bracket C times B. All right, so let's take a look at this, and let's write down the first one. So C bracket cross C, and then put that in bracket A, right, like that, vector cross B vector equals 2, and this equals 2, and now this is going to be, again, everything would do the same thing, cross product, but we also have a C there now. So now we have a C times by A to B B3 minus, again, similar to this cross product here, A2, B3, but we also have a C there. And the next one is going to be, again, CA3, B2. So we have that constant there. The next one's going to be CA3, B1 minus A1, B3, and then the next setup is, it's going to be C A1, B2 minus C A2, B1. Like that. Alright, now that we have all this, we could just factor out the C. So we could factor out the C, and that becomes, well, our usual cross product. A2, B3 minus A3, B2, and then we'll have A3, B1 minus A1, B3, and then A1, B2 minus A2, B1, like that. In other words, this just equals to C times bracket A cross B. So we got this first, the first part, or the middle section there. Move this down and put a bracket, and we got this correct. Now the next setup is, well, instead of factoring it out, we could just move the C over into this B side. So this becomes A2, C B3 minus, and then A3 C B2, and then put a bracket and put a comma for the next component. And then we'll have A3 C B1 minus A1 C B3. Next one's going to be A1 C B2, and the next one's going to be A2 C B1. In other words, we just, yeah, it's exactly the same thing as the other one. Move this over. Yeah, so now what we get is this just equals 2. Now we have A, but now we have C is multiplied by every single one of the B's, the B vectors. So that's the vector inside it. So this just equals to A, here, fix that up. A vector cross, and then bracket C scalar times by B vector, like that. And that is a correct proof, and that's exactly this part right here. Alright, so now this brings us to exercise 3, and this one states prove property 3 of theorem 3, and that's this one right here, A cross B plus C, and then show that it equals to, well, just expand this out, A cross B, and then plus A cross C. So let's take a look at this, and let's just write this out in our typical determinant format. So A cross, then B plus B vector plus C vector, like that. We could write this as, in our IJK format, I'm going to put like this. I'll put an I there. Yes, this is going to be our I vector. Next one's going to be our A1. And now these ones here, we're just adding these. So that each component is going to be, well, B1 plus C1. All right, now the next setup is J. It's going to be A2, and then we're going to add B2 plus C2. So that's all the adding is. You're just adding each component. And then the next one is K, like that. It's going to be A3, B3 plus C3, like that. And then we're going to do our determinant format, and then we'll do the I, cross out, like this, and then you'll have this A2, etc. I'll put this all in there. Instead of putting the IJK, I'm just going to put this in this bracket format. I like this one better. So we'll have A2 times B3 plus C3. We'll have A2 times B3 plus C3. All right, and then minus. So the minus is this one right here. A3 times, so A3 times by B2 plus C2, like that. Then I'll put a comma. Now the next setup is the J component, and I cross this out, and that's going to be, well, it's going to be negative Yeah, it's going to be negative. Let's put a negative just for show. So we're going to negative a1 times b3 like that. And I'm gonna put a square bracket. A1 times by B3 plus C3 minus, and this one right here, A3 times by B1 plus C1, like that. Close bracket, like that. All right. And erase this all. Next setup. K, cross out. And we're gonna go A1 times it by B2 plus C2 minus A2, then B1 plus C1, like that, close bracket. So that's what we have now. And now what I'm going to do is I'm going to expand these out. So this equals to A2 times B3, A2 times B3, plus this A2 plus C3, but instead of typing it there, I'll put it afterwards. So this times this, I'm going to go from here, minus A3 times B2. Put that here. Put it all in one go, and then now the next one, A2 plus C3. Plus A2 C3, and then this one here, A3, and then this is going to be negative, because these are the negative ones, and negative A3 C2. Negative A3 C2. And now the next setup, we're going to do exactly the same thing here. So I'm going to subtract this by, so A1 B3, so A1 B3, and then A3 B1 minus A3 B1, and then A1 plus, A1 times C3, plus A1 C3, and then this one minus A3 times C1. Like that, in bracket. Alright, so like that. Now the next one, the next one here is this part right here. So A1 B1, A1 B2, and then minus A2 B1 equals to plus A1 B2 minus A2 B1, and then the next one A1 plus C2 minus, and then A2 times C1. Like this. Close it. Alright, so now we have all this. And now notice what we have. We have this, and these are all separate. In other words, so all these components right here, A2 B3 minus A3 B2, then this one right here, with this negative sign, A1 B3 minus A3 B1, then A1 B2 minus A2 B1. This is equal to A cross B, like that. And then all we're doing is adding now. We're adding a plus on every single one here for this A2 C3, and then minus A3 C2, and this A1 C3 minus A3 C1, and so on, and this A1 C2 minus A2 C2. In other words, we're adding A cross C. So this is exactly what we just proved, and what we were asked to prove. So you could just FOIL this out, so multiply or expand this out. A cross B, A cross and bracket B plus C is equal to A cross B plus A cross C. Alright, so now this brings us to our attention to exercise 4, and this one states proof property 4 of theorem 3, and this is, it's almost identical to this one, but instead of A cross B plus C, we have it the other way around, A plus B cross C, and show that you could FOIL this out exactly, so A cross C plus B cross C, so basically the other way around. So we could do basically the same setup here. We'll just copy and paste exactly the same thing here, but slightly different. So we'll go A plus B, and then cross C. Write this out in the determinant form. So we'll put I, and now instead of the bottom one there, so the top one is A plus B, so A1 plus B1. And then the bottom's going to be, well, it's going to be C1. And then the next one's going to be J. and this is going to be J vector. This is going to be A2 plus B2, and then C2. And the next one's going to be A3 plus B3, C3, like that. Cross. Yeah, then we have this, and then we're going to do the same setup here. This equals 2. Put this here. So I'll have this, cross this out, and now we're going to have this setup here. A2 plus B2 times by C3, like that. I'm going to put the C3 there, and then minus this part right here, A3 plus B3 times by C2, like that. So again, it'd be exactly the same setup, and then just a comma. The next setup now is the J component, cross, cross. We will go with now A1 here times that, put a negative, A1 plus B1 times by C3 minus A3 plus B3 times by C1. And then put a bracket here. Yeah, this is actually this bracket. Like that. Just good to have that negative there. And the next one is going to be the K component. K like this. Cross, cross. And then we're going to have A1 plus B1 times by C2 minus A2 plus B2 times by C1. Like this. And then close bracket. Or the triangle bracket like that to indicate the components. And then again, expand this out. It's going to be A2 plus, no, or A2 times by C3. So multiply this and this, and then we'll do this and this. Minus A3 C2. And erase this. Then we're going to do this and this. And this is going to be B2 C3. And then we're going to go this and this. Minus B3 C2, like that. And that is, yeah, that's just expanding it out. Put this like this. I forgot to do the close bracket. Like this. And then the next one is similar to here. Put a negative there. And then C, erase this. C3A1, C3A3. So we'll get, put this bracket A1, C3 minus A3, C1. Now the next one is inside here, plus B1, C3, and then this one here, minus B3, C1, bracket. All right, now we are powering through it pretty efficiently. Next one is C2A1, C1A2. So we'll get A1, C2, and then minus A2, C1, and then erase this. We'll go C2, B1, and then plus this is B1, C2, and then this one is right here, minus B2, C1. Close it like that. Alright, so now we have this. Yeah, we have this, and we can see again the same thing. This is A2, C3 minus A3, C2. There's this negative, and then A1, C3 minus A3, C1, then A1, C2, etc. That's just A cross C. This equals to A cross C. And then the next one is going to be, well, we're adding these B2, C3 minus B3, C2, etc. B1, C3. B3, C1, and then B1, C2, etc. Plus, this is going to be B cross C. B cross C. Then circle all this. And it's check mark. So exactly same as before, but we just start from the, this one at the bottom, another one at the top. Yes, fascinating. So A cross C plus B cross C. Fascinating stuff. Alright, and now this brings us to the last part of this giant long video as per usual. So exercise 5, and this is the vector triple product, and this is again property 6. So prove property 6 of theorem 3, and this one is it states right here, A cross, then bracket B cross C, show that it equals to A dot C times B minus A dot B times by C. All right, so there's a lot of cross products and vector products. So basically going from cross product to dot products and subtraction. So let's go and write this out. All right, so we have, let's just write this down in our determinant format, x cross bracket b cross c, and now this is going to equal to, well, we have our I, and now it's going to be an interesting one because we're going to have a1 here, and now let's just do this all in our head, b cross c, put this underneath here because we're going to do a cross product of it again. Let's just do this here. So b2 c3 minus b3 c2. Then the next one is going to be j, and the j one's going to be, this is going to be our our a2. So this is our a2, and let's just do this without the negative sign, because when you put the negative sign, it's going to be like this b1 c3, etc. But let's remove it. So we'll start off, instead of b1, we'll do the b3 c1 minus b1 c3. And then the next one is k, and this is going to be a3, and let's just shift everything over here and move this here. This is going to be b1 c2 minus b2 c1 and close bracket. All right, so we have this and we have that. All right, the next setup is, let's just expand this all out, and we'll do this all relatively quickly here. I'm going to go to the first term. I'm going to use my trusty square bracket or the triangle bracket. I'm going to cross this out, and we'll just expand this all out in one go. So we're going to go a2, b1, c2, b1, c2. Next one's going to be a2, b2, c1. And then subtracted by, we have this a3, b3, c1, then minus, but then we're already subtracting, so minus cancels. There's a positive, a3, b1, c3, like that. And comma. Now the next one here, this next one, well, we're doing a cross product of this. We already sorted out the negative here, but we're doing another cross product, and we're going to have to add the negative, and it's not that straightforward to change it up right now. To switch it up to get rid of that negative, but so we'll just do it with it. So we're going to go this component, cross this out. Now we're going to have a negative, then bracket a1 times this setup here. A1, B1, A1, B1, C2, minus A1, B2, C1, and then we're going to go minus, and then this is going to be A3, B2, C3, minus, but then there's going to be minus, another minus, it's going to be positive, A3, B3, C2, and then close bracket, and then comma. Then next component is this one. Next component is this one. Fix up this arrow. Is this cross it out. Next one, we're going to have A1 times by this setup here. So A1, B3, C1 minus A1, B1, C3. And then we're going to have a minus, and then A2, B2, C3, and then minus becomes positive, plus A2, B3, C2, like that, and then triangle bracket like that. Alright, so now that we have this, and what we're going to do now is I'm going to put all the positives on one side and all the negatives on separate from it, and then we'll also do some more algebra here, just to illustrate some very interesting properties here. So this equals 2, and then put this triangle bracket like this. And then we'll put, this is the positive one, so we'll have this A2, and I'll write this here, let's write this here, A2, B1, C2, and then plus right here, A3, B1, C3. And now the next one is going to be, we'll have these minus right there, minus A2, B2, and then we'll have C1, and then there's a minus right here, minus A3, B3, C1. And before we get further, I just want to note some very interesting stuff right here, because if we factor out this B1 and this B1 right here from here, we'll have an A2, C2, and an A3, C3, and that's pretty much the dot product, where you have the components multiplied and then you add up. So multiply A2 times C2 plus A3 times C3, etc. But we're just missing A1 and C1. And likewise here we have a 2, so A2, B2, if we factor out the C1, we're going to be left with A2, B2, and then this is going to be minus, right here, minus A3, B3. So this is also a dot product with a negative sign, but it's missing one piece. So what I'm going to do now in this case, just to illustrate, because it's going to be the same for all of these ones, as you can see, there's an A1, B1, and there's a C2. A1, C1, and then there's a B2. So these ones all have pretty much dot product properties. So what I'm going to do is, I'm going to shift this over. So I'm going to shift this over, make some room. Let's put this right here. Put a comma. And this one also I'm going to shift this like this, just to make some room. Write this all smaller. Or actually here, I just shifted it over, made it smaller. And then now we'll write this in red. I'm going to put this right here, red. And I'm going to do right here is I'm going to add A1, C1. So A1, A1, put the B1 right here. C1, like that. And then so we're going to add that to it, but we're also going to subtract it as well. So this was a minus there. And we're going to put let's put a minus right here. A1, B1, and then C1, like that. So we're just going to do the exact same thing. So we're not changing anything. We're just adding that and go back to this negative sign like that. So now that we have that, then when we factor it, we will get the dot product. But anyways, we'll get to the next setup here. So now the next one is this negatives. And this one's pretty much the same thing. So we're going to get, let's do all the positives on one side and all the negatives on the other side, and also add these extra ones to fill in the blank. So here we don't change anything, as these just cancel. It's the same thing, but it will help in our dot product formulation. So now the next one is this middle one. So we put the negatives here, so all the negatives become positive. Let's write that down. So this one's going to be the positive. These two are the positives, and then the other ones are the negatives, because we're minus and multiplying by this negative. So we're going to have, this is going to be A1, B2, C1. And now the next one is A3, B2, C3, but then that's missing an A2, C2. So we'll just add that. We'll add that soon. So we'll put this plus right here. A3, B2, C3. Because we're going to factor out the B2s. And then the next one is, these ones were positive. They become negative because it's a negative sign. This becomes negative A1, B1, C2. You see the pattern? And then this one right here, minus A3, B3, C2, like that. We'll actually shift this over. Put this all the way here and make this smaller to fit in. All right, so we have that negative there. And then we'll put this in red and write it in red, the missing piece, which is A2, B2, C2. So we add that plus, and then we subtract it so we don't change anything. A2, B2, C2. All right. Now we're getting the hang of it. Now the next one is this part right here, write this in black. A1, so we'll have A1, B3, C1. And then A2, B3, C2, plus A2, B3, C2. And then we'll just leave a big blank here. We're going to have to use that in red for the ones we're adding afterwards. And now the next one is going to be these negatives right there. Negative A1, B1, C3. And minus A2, B2, C3. And now the next ones, these ones are going to be plus, minus to get the A3s, etc. All right, put this in red. This is going to be plus A3, B3, C3. And now the next one right here, minus, so we're getting rid of that, A3, B3, C3, like that. And put this in black. And we don't need this anymore, just cancel that. Alright, so now that we have this, now we're going to factor out, we're going to factor the C's and the B's in the corresponding positive or negative setup. So this equals 2. So factor that out, we're going to be equals to right here, bracket A1, B1 plus A2, A2, C2. Actually, yeah, this is A1, C1, I mean. Because we're factoring out the B1s. B1, B1, B1. Alright, get rid of this. So that's going to be A1, C1, and then A2, C2. And then the next one is A3, C3. And then put this as B1. Now we're going to subtract here. Subtract this by, and we're going to factor out the C1s. So it's going to be subtracted, and then we put this minus and put a bracket so that it all becomes positive when you take the negative out. A1, B1 plus A2, B2, and then plus A3, B3. And then bracket C1, comma. Now we do the next one. So that was the I basis vector. Now we're going to do the J or the Y coordinates and then do the Z after. So the next one is right over here. So A1, B2, C2. Yeah, so we're going to factor out the B2s. The next one's the B3s and so on. And then this one's C2, C3s. All right, let's do that. This is going to be, this one's going to be A1, C1 plus A2, C2. And yeah, it's the exact same thing as above. A3, C3. And then this is going to be B2, like that. Minus, same thing. A1, B1, minus, plus, because we're taking the negatives out. A2, B2 plus A3, B3. And it's going to be C2, like that. The next one is going to be now the B3s and the C3s. Now this is going to be A1, C1 plus A2, C2 plus A3, C3. Then B3 minus A1. Yeah, it's pretty tedious. Yeah, so like this B1 and then plus A2, B2. It's tedious, but just because I didn't want to skip any steps or too many steps here. So just to illustrate this. And then a square bracket like that. So now that we have this, and now we could realize, well, this is just a dot product. This is A dot C, this one's A dot B, because remember you just multiply the components and add them up. So in other words, we just get A dot C, and this one's A dot B there. So let's just write it all out. This equals 2. It's going to be, and I'll just make it even simpler. Yes, we'll have A vector dot, and remember, the dot product gives a scalar. It just gives a number. So this is A dot C, like this, and then times it by B1. The next one's going to be minus, and then this is going to be A dot B vector. This is going to be C1. And the next one's going to be A dot C. Again, these are all the same. A dot C. Then B2 minus A dot B. C2. And let's make this smaller. Like this. Move it over. The next one's going to be A dot C dot, A dot C, B3 minus, just shift that over, so minus is going to be A dot B, and then this is C3, like that. So these are all the, these ones are all just the A dot B's, etc. And so on, the other one's A dot C. Alright, so now that we have all this, and then let's just put it all in compact form, and this is just, again, dot product, it's just a scalar. And then this is now this is all in vector form. In other words, dot product is multiplying it by the B vector and then subtracting it by this dot product times it by the C vector. So that's exactly this proof right there. So this equals to, this whole thing equals to A dot C dot B, and just multiplied by the B vector. So we get this scalar into a vector. So you're multiplying this vector by the scalar and subtract it by A dot B, and then C vector. Yes, that's exactly our proof right there. So this is a vector triple product right here, vector triple product. So this A cross, and then A cross bracket B cross C equals to A dot C times B minus A dot B times C. And this is the times because this is a scalar. But then the dot product is this is the multiplication method, or the similar to, or the analogous to multiplication, but with two vectors. So two vectors, dot product equals to a scalar, and now you're doing a scalar multiplying a vector. Hence, you don't need the dot product for those. But yes, this is what we have. Double check in A dot C, B minus A dot B, C. So A dot C, B minus A dot B, C. Anyways, that is correct. Yeah, so and that is all for today. Hopefully you enjoyed and followed through another epic long math easy video. Let's just scroll up. And yeah, and like always, you can download these exact notes in a link in the description below, as well as viewing all these notes in article format on the Hive blockchain. The links will be in the description below. And also just shout out to my MES Links Telegram channel. If you want to follow what I do in real time, I just upload a bunch of info, memes, conspiracy stuff, math stuff, and just random stuff. If you're open to exploring new information, and also what's going on in my brain as I go through a bunch of info. Anyways, that's all for today. Thanks for watching, and stay tuned for another math easy solution.